Suppose we have a function of three variables being x, y, and z, and that's defined on a closed bounded region in 3D space, which we'll call S. So an example being this tetrahedron. Now if we take a box surrounding this region and partition it using planes that are parallel to the coordinate axis, then we end up with rectangular cells. And if we take the cells that are completely lying inside the region S and index them, then the volume of the rectangular box I is the dimension in the x direction by the dimension in the y direction by its dimension in the z direction. And if we choose some point in each cell with coordinates xi, yi, and zi, then we can write the Riemann sum as the sum of the rectangular cells that are completely inside S. So we have n rectangular cells, and we sum the function evaluated at the point with coordinates xi, yi, and zi, multiplied by the volume of cell I. So again, if we take the limit of the Riemann sum as the number of cells approaches infinity, or the largest dimension approaches 0, so essentially the volume of the cells tends to 0. So if the same limiting value is approached despite the Riemann sum, meaning it doesn't matter which point we choose to evaluate the function in each cell and how we partition the region, then the function is said to be integrable over S. So therefore, if the function is continuous and the bounding surface of the region consists of finitely many smooth surfaces that are joined together by finitely smooth curves, so here we can see the tetrahedron has 4 triangular surfaces. So these two surfaces, for example, are joined by a line which is continuous. So in this case, the Riemann sum approaches the same limiting value, being the triple integral of the function of x, y, z over the volume of the region. And similar to double integrals, we can write this as an iterated integral. So we have the triple integral over our solid region of the function of 3 variables integrated successively over x, y, and z, and not necessarily in that order. And again, similar to double integrals, in the special case where the function is constant and equal to 1, then we have a volume integral over that region. So basically the triple integral over the volume of the solid gives the volume of the region S. We can evaluate the triple integral of our function of 3 variables, being x, y, and z, over the volume of a solid region using the 3-dimensional analog of Fubini's theorem. So in this first example, we'll first integrate with respect to z, then y, then x. So first we sketch our solid region and project it onto the xy plane. So what you'd get is the shadow of this triangular base of this tetrahedron. And first we'll integrate our function of 3 variables with respect to z. So to find the z limits of integration, we take some point in this planar region R and then draw a line through this point parallel to the z-axis. So this line cuts the bottom surface of the tetrahedron and this front surface. So our lower limit of integration is the function defining this bottom surface, So it'll be a function of two variables. So that's our lower limit of integration, being where this line enters the region, and we get our upper limit of integration where the line exits the region. So this bounding surface is defined by another function of x and y, which is our other limit of integration. And next we integrate over y. So what we do is draw a line that's parallel to the y-axis. So in this case, our lower bounding curve is a function of x. So we have y is g1 of x. So that's our lower limit of integration. And our upper limit of integration is the function defining this line, or in generally a curve. So that would also be another function of x, which is the upper limit of integration. So noting that's where the line enters and exits the region. And finally, we integrate over x. So that will be from x equals a to x equals b, to include all these lines. Now in this second case, we see this right face of the tetrahedron is parallel to the xz plane, so therefore we'll project the tetrahedron onto the xz plane. So our projection, or shadow of the tetrahedron, looks like this. So that's our solid region, and this is our planar region R. So in this case, it's more convenient to first integrate with respect to y, then either x or z. So in this example, we'll integrate with respect to x and then z. So if we first integrate our function of x, y, and z with respect to y, then we essentially select a point in the planar region and draw a line that cuts through the solid. So in this case, our lower bounding surface is this surface over here, where the cutting line enters the region. So this surface will be defined by y as a function of x and z. So that's what we'll get for our lower limit of integration. And our upper limit of integration is where this line exits the region. So that will be y as another function of x and z. So that's our upper limit of integration. And next we'll integrate with respect to x. So essentially, we draw a line through region R that's parallel to the x-axis. So our lower bounding curve is x as a function of y. So where this line enters the region is our lower limit of integration. And the upper bounding curve is x is equal to another function of y. So where this line exits the region is our upper limit of integration. And finally, we integrate over z. So in this case, we integrate from z is equal to a, being the origin in this case, to z is equal to b, to include all these lines in the region. So that's the tricky part, which you'll get used to, and then evaluating the triple integral will be straightforward, as we'll see in worked examples. Find the volume of this tetrahedron, where the vertices are given. So we first project this tetrahedron onto the xy plane, so the shadow looks something like this. And recall our volume integral was the triple integral of our function, where the function is equal to 1, integrated over the volume of the solid region. So here it's convenient to first integrate with respect to z, and then either x or y. So we'll then integrate with respect to y and then x. So we choose a point in this region and draw a line that cuts the solid parallel to the z-axis. So integrating with respect to z first, and observing that this line cuts the solid region at z is equal to 1, and then the line exits the region through this face of the tetrahedron. And I'll leave it for you to obtain the equation of the plane representing this surface being the dot product between a normal vector and the vector between 2 points on the plane, which is equal to 0, and you'll be able to obtain the following equation for the plane of this face. So that's x minus 3 plus y minus 0 plus z minus 1 is equal to 0. So if you solve this equation for z, you get the upper limit of integration, which is z is 4 minus x minus y. And next we integrate over y. So if you draw a line parallel to the y-axis, our lower limit of integration is that y is equal to 0, and you can obtain the equation of this line in the xy plane. So we have x is equal to 3 and y is equal to 3. So the equation of this line is y is equal to the slope of the line, which is minus x, plus the y-intercept of 3. So the upper limit of integration is 3 minus x. And finally, we integrate over x, which gives the volume of the solid. So to include all these lines, the lower limit of integration is at x equals 0, and the upper limit of integration is at x equals 3. So another way to look at this is we're summing up the volumes of these infinitesimal cubes in the z direction. So we get a column of cubes defined by a function of x and y, and then we sum this column of cubes in the y direction. So we get a wall of cubes defined by a function of x, and then we sum this wall of cubes in the x direction to get the volume of the solid. So evaluating the inner integral with respect to z, we get z evaluated at z equals 1 and 4 minus x minus y. So evaluating this, we get 4 minus x minus y minus 1, which is 3 minus x minus y. And then we integrate this from y equals 0 to y equals 3 minus x over y, and integrate this result over x. So what we get is 3y minus xy minus y squared on 2, evaluated at y equals 0 and 3 minus x. So we get 3 by 3 minus x by 3 minus x minus 3 minus x squared on 2, and the remaining terms will evaluate to 0. And if we simplify some of these terms, we get 9 minus 3x minus 3x and plus x squared, and minus 3 minus x squared on 2. And that's integrated from x equals 0 to x equals 3. So what we get is 9x minus 6x squared on 2 plus x cubed on 3 and minus 3 minus x cubed on 2 by 3. And we evaluate this at x equals 0 and x equals 3. So what we get is 9 by 3 is 27, minus 3 by 9, which is 27, plus 27 on 3, which is 9, plus 3 minus 3 cubed on 6, which is 0. And the next terms evaluate to 0. And finally, we get minus 27 on 6. So that's equal to 9 minus 9 on 2. So the volume of the tetrahedron is 9 on 2. Find the volume of a region between the two given paraboloids. So we recognize we have one standard paraboloid and the other paraboloid will be inverted. So to find the intersection between the two paraboloids, we set them equal to each other. So we have x squared plus y squared is equal to 8 minus x squared minus y squared. And therefore, we get 2x squared plus 2y squared is equal to 8, or x squared plus y squared is equal to 4. So if we substitute for x squared plus y squared in either of these equations, we get z is equal to 4. So that's our intersection curve, being a circle at z equals 4, and it has a radius of 2. So our bottom paraboloid looks something like this, and our top paraboloid looks something like this. So that's at z equals 4 and z equals 8. Now to find the volume of the solid region, we project the paraboloids onto the xy plane. So the shadow looks like a circle with a radius of 2. So what we'll do is integrate with respect to z first. So if we take a point inside this planar region and draw a line through our solid, the line enters the solid at z is equal to x squared plus y squared, being the bottom paraboloid, and exits the solid at 8 minus x squared minus y squared. And then we can either integrate with respect to y or x. So if we draw a line through the planar region, being the circle, then from this equation, we have y squared is 4 minus x squared, and therefore y is plus or minus the square root of 4 minus x squared. So this is the back half of the circle, giving the lower limit of integration being minus the square root of 4 minus x squared. So that's where the line enters the region, and the line exits the region at the other semicircle, having an equation of root 4 minus x squared. And finally, we integrate over x from x equals minus 2 to x equals 2 to cover all the lines in that region. So that's our triple integral. So integrating with respect to z, we get z evaluated at x squared plus y squared and 8 minus x squared minus y squared. So what we get is 8 minus x squared minus y squared minus x squared minus y squared, which is 8 minus 2x squared minus 2y squared. And then we next integrate with respect to y from minus root 4 minus x squared to root 4 minus x squared. So what we get is 8y minus 2x squared y minus 2y cubed on 3, evaluated at minus root 4 minus x squared, and root 4 minus x squared. So let's expand this over here. So we have 8 by 4 minus x squared to the half minus 2x squared by 4 minus x squared to the half, and we have minus 2/3 of 4 minus x squared to the half cubed. And then we have minus 8 by root 4 minus x squared. So that gives us 16 here. And minus 2x squared by minus root 4 minus x squared, which gives a positive value. And then subtracting this, we get minus 4x squared here. And the next term is a cube term. So 2 minuses is a plus. So we subtract another 2/3 from this term. And this result is integrated from x equals minus 2 to x equals 2. And now we can evaluate this using trig substitution. So if we take cosine squared theta plus sine squared theta is equal to 1, and subtract sine squared theta from both sides, so we get cosine squared theta is 1 minus sine squared theta. And if we multiply through by 4, so we get 4 cosine squared theta is equal to 4 minus 4 sine squared theta. And let x equal 2 sine theta. Then we get 4 cosine squared theta is equal to 4 minus x squared. And we can substitute for 4 minus x squared and simplify the integral. So 4 cosine squared theta to the half is 2 cosine theta. So that gives 32 cosine theta. And minus 4x squared, where x squared is 4 sine squared theta, multiplied by 4 cosine squared theta to the half, which is 2 cosine theta. Then we get minus 32 sine squared theta cosine theta. And finally, we have 4/3 by 4 cosine squared theta to the 3/2. So 4 cubed is 64, and taking the square root gives 8. So 4 by 8 is 32, and cosine squared theta to the 3/2 is cosine cubed theta. And finally dx is 2 cosine theta d theta. So we can break this up into 3 integrals. So we get 64 by the integral of cosine squared theta. We're using the double angle trig identity, is 1/2 plus 1/2 cosine 2 theta. And our next integral is minus 64 by the integral of sine squared theta by cosine squared theta. So that's 1/2 minus 1/2 cosine 2 theta by 1/2 plus 1/2 cosine 2 theta, which gives 1/4 minus 1/4 cosine squared 2 theta. And our next integral is minus 64/3 by the integral of cosine theta to the power of 4, which is cosine squared theta by cosine squared theta, or 1/2 plus 1/2 cosine 2 theta squared over theta. And if we simplify these two integrals, we factor out 1/2. So 64/2 is 32. And factoring out the 4, we get 64 on 4, which is 16. And cosine squared 2 theta is a half plus a half cosine 4 theta. And 1 minus a half is a half. And if we factor out a half, we get 8 by 1 minus cosine 4 theta. And if we simplify this integral by first expanding it, we get a quarter plus 2 by a half cosine 2 theta plus 1 on 4 cosine squared 2 theta. So this term here is 1 quarter by 1 half plus a half cosine 4 theta. So therefore we can simplify this integral. So we get 1 quarter plus 1/8 is 3/8 and plus a half cosine 2 theta and plus an 1/8 cosine 4 theta. And simplifying a bit further, 1 half is 4 on 8. And if we factor out 1 on 8, we get 64 on 8, which is 8. So this becomes 3, this becomes 4, and this becomes 1. And now we need to replace our limits of integration, because we're integrating over theta. So when x is equal to minus 2, we get sine theta is equal to minus 1. So arc sine theta gives theta is equal to minus pi on 2. And when x equals 2, sine theta is equal to 1. So arc sine theta gives theta is equal to pi on 2. And now we can evaluate these three integrals. So we get 32 by theta plus a half sine 2 theta, evaluated at minus pi on 2 and pi on 2, and minus 8 by theta minus 1 on 4 sine 4 theta, evaluated at minus pi on 2 and pi on 2, and minus 8 on 3 by 3 theta plus 4 on 2, which is 2 sine 2 theta, plus 1 on 4 sine 4 theta, evaluated at minus pi on 2 and pi on 2. So sine 2 pi on 2 or minus 2 pi on 2 is 0, so we can just ignore these terms. So what we get is 32 by pi on 2 minus pi on 2, which is pi, and minus 8 by pi on 2 minus pi on 2, which is also pi, and minus 8 on 3 by 3, which is 8, by pi on 2 minus pi on 2. So the volume of our solid between the two paraboloids is 16 pi. Write the integral to find the volume of a region between the two paraboloids as an iterated integral over y first, then x, then z. So recall when we integrated over z first, we can evaluate the integral as a single integral by projecting the solid onto the xy plane. But this time, because we're integrating over y, we're going to project the solid onto the xz plane, being perpendicular to the y-axis. So on the xz plane, where y is equal to 0, we have z is equal to x squared. So that's from z is equal to 0 to z is equal to 4. And another parabola at y equals 0 with the equation 8 minus x squared. So let's just draw this over here, where we have the xz plane. So the bottom parabola is like this, up to z equals 4. And the other parabola looks something like this, up to z is equal to 8. So to integrate over y first, we take a line that's parallel to the y-axis, so that enters the region at this point and exits the region at this point. So if we write the equation for the paraboloid in terms of y, we get y is plus or minus the square root of z minus x squared. So our first integral is from minus the square root of z minus x squared to the square root of z minus x squared with respect to y. So that's the integral over y, and then we integrate over x. So from this equation, we get x is plus or minus root z. So if we take a line along the x-axis, this enters the region at minus root z and exits the region at x is equal to plus root z. And finally, we integrate over z. So to cover all these lines, we integrate from z equals 0 to z equals 4. So that's our first integral. And the second integral, from z equals 4 to 8, is evaluated in a similar way. So we take a line parallel to the y-axis that enters and exits the top paraboloid. So writing this equation in terms of y, we get y is plus or minus the square root of 8 minus z minus x squared. So our first limit of integration is that y is minus the square root of 8 minus z minus x squared to the square root of 8 minus z minus x squared. And then we integrate over x. So we take a line parallel to the x-axis and write this equation of the parabola in the xz plane in terms of x. So we have x is plus or minus the square root of 8 minus z. So this line enters the region at minus the square root of 8 minus z and exits the planar region at the square root of 8 minus z. And then to include all these horizontal lines, from z equals 4 to 8, we integrate from z equals 4 to z equals 8. So we're evaluating the volume of the solid in this case, piecewise, which is more tedious than integrating with respect to z first. Let's evaluate the following triple integral. So first we're integrating over x from x equals y to x equals root pi. So we have x equals root pi somewhere here. And we can draw in our line x equals y by taking y is equal to root pi. So this is our line x equals y. And then we're integrating from y equals 0 to root pi. So if we take our lines parallel to the x-axis, we're integrating these from y equals 0 to root pi, which covers this entire region. And note that these two equations are equations of cylinders, with the base of the cylinder being a line, or equations of a plane that's parallel to the z-axis. So we can draw our first cylinder like this to z equals 8, and our other cylinder at x equals root pi, where the base of the cylinder is in this region, looks something like this. So this is also at z is equal to 8, but further out of the screen. So our solid region looks something like this. Now we can't integrate with respect to x first, because we can't evaluate the integral of sine x squared. So what we'll do first is integrate our function with respect to z first. So we have sine x squared on z to the third integrated over z. So if we take a vertical line through this solid, it's always going to enter the region at z equals 0 and exit the region at z equals 8, no matter where we draw that line. And then we can integrate with respect to y. So this projected solid onto the xy plane has this base, and to integrate with respect to y, we just draw a line through this planar region. So that enters the region at y is equal to 0 and exits the region at y is equal to x. And then finally, we integrate from x equals 0 to x equals root pi to cover that entire region. So the integral of z to the minus a third over z gives z to the 2/3 on 2/3, so we have 3 on 2. And that's multiplied by sine x squared, evaluated at z equals 0 and z equals 8. So cube root 8 is 2, squared is 4. And 3 by 4 is 12, on 2 is 6. So we have 6 sine x squared. And when z equals 0, the entire term is 0. So we integrate this term with respect to y from y equals 0 to x. So what we get is 6 sine x squared by y evaluated at 0 and x. So that gives 6x by sine x squared minus 0. And we integrate this result over x from x equals 0 to root pi. So using u substitution, we can now evaluate this integral. So setting u equal to x squared, du is 2x dx. So what we get is 6 on 2, which is 3, by the integral of sine u over u. And when x equals 0, u is equal to 0. And when x is root pi, u is equal to pi. So what we get is 3 by minus cosine u, evaluated from u equals 0 to pi, which is equal to 3 by minus cosine pi, which is minus minus 1, and minus minus cosine 0, which is 1. So the triple integral evaluates to 6.